next video in our series all about Gauss's law. In the previous video, we went over electric flux, where we were looking at the A field going through a window. But now we're going to take that idea and we're going to apply it to different kind of scenarios. So this is Gauss's law for a closed surface. Let's begin. So the first thing I want us to do is to draw a point charge. Yeah, let's draw a point charge there, and let's draw the E field lines going out of the point charge. I'm just gonna draw, not too many. All right, just happy E field lines here, happy E field lines there, happy E field lines everywhere. All right, that's pretty good model of a positive charge with the E fields emanating out. A couple of things that I want us to write here, and we will call these true statements. We will say that the E field formula for this situation is KQ over R squared, meaning we have a E field that as we go out radially, it gets weaker. And for the sake of the future, where we're going to get some calculus in, I'm going to rewrite K to be 1 over 4 pi epsilon naught. Oh, yeah. So that's a different way that you can write K. I know we wrote K as 9 times 10 to the ninth, but you'll also see this written on your formula sheet. Q over R squared. Wonderful. All right, so with that out of the way, let's apply what we learned about the flux to the situation here. So if you remember from the previous video, I was talking about these windows, right? These areas for the flux to go through. So in order to do the same idea here, we have a problem, right? We have a situation. In the previous scenario, all of our field lines were just going in the same direction. And so it was easy to capture all of these E fields. We would just place a window right here, and we would say, all right, E field lines just go straight on through, and they did. And we would say, ta-da, 100% flux. But here we have E fields going everywhere, and so we could draw it like this, right? And then that would capture some of the E fields, so that doesn't really work. Okay. And so what we're going to do is, through the power of a calculus, we are going to draw one teeny tiny window right there. Okay, so that teeny tiny window will have this E field going through it, pop, 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 like that. But you might be thinking to yourself, wait a minute, Shirley, there are more E fields from this point charge, and you'll be right. So I would draw a teeny tiny window here, and then we'll have this E field going through that teeny tiny window. And then we're just going to repeat this process. We're going to draw these teeny tiny windows all throughout this surface here, okay? And you know what? This here is just a model of a point charge with E field lines emanating from it. Technically, this model will be best represented with an infinite amount, right? I say infinite, but you know what I mean? A lot, like porcupine style, a lot of E field lines emanating from this point charge. So what we have to do is we have to have a teeny tiny window for all of those E field lines. And so if you do that, I'm not going to draw it there, but what happens is if we draw these teeny tiny windows throughout, what we end up with is a circular drawing. We should look at that. Look at all those teeny tiny windows. Okay. But if you're really thinking, you're thinking, wait a minute, Mr. Lee, this is a 2D image. Aren't point charges, don't the E fields emanate from a 3D direction? And you'll be correct. So this isn't a circular closed surface. This is actually a sphere. And so, welcome, friends, to your first Gaussian object. This is your Gaussian sphere. And it is our first closed surface. So yeah, On the screen, it does look like a circle, but trust me when I say it is a 3D object, it is a sphere. So let's go over how we can apply math to our verbalization of what just happened. Okay, so we know that the formula for flux is equal to E dot A, right? Both of those vectors, and remember that dot product represents cosine of theta. But what we did is we didn't have a defined area. Okay, what we did is we took many teeny tiny areas. And if you're familiar with calculus, whenever we do many teeny tiny things, that is the same as doing a dA in this situation, right? So we took teeny tiny windows and we put them all throughout this point charge so that we have a spherical object, right? And so you might be thinking, well, did we change the E field? And we didn't, right? We didn't mess with a single thing about our E field, so the E field doesn't change. Our E field in this situation is constant. So I'm going to write here, this is a constant, and this represents the tiny windows. These are the tiny windows. So with this, we can now apply our knowledge of calculus to come up with the calculus version of flux. And we end up with flux is equal to, watch what we do here, brand new symbol alert, whoa. That is called the surface integral, whoa, of the E field dot product dA. All right, so let's give ourselves some definitions. So let's see, this new symbol, this is called the surface integral. So what this means is that we're taking the integral across the entire surface, and in this case, our entire surface is the shape. And this also tells us, this is very important, the surface must be closed, okay? Because we need to have a starting surface, or starting point of the surface and end, and it must, from start to finish, we need to have a closed surface. We can't have any open areas. Very important. And the idea behind that is we have to have teeny tiny windows encasing our point charge. We can't leave a single point that does not have a teeny tiny window. So the surface must be closed. So important. I'm going to highlight it. Okay. And this surface integral and the dA refers to the surface area of the shape. Okay, and the shape in our situation is a sphere. All right. So with our formula here, let's actually take a look at what we can do. Oh, before we move on, I don't want to move past this idea here where the E field is constant. Okay, so let's go back to this drawing. So we see here that we drew teeny tiny windows spread throughout, and I can make this statement that we drew our teeny tiny windows that is equidistant from the charge. Okay, so I'm going to write that down. Our dA is equidistant from the charge. Okay, and because we said that, and this is a single point charge, because of this statement, we can say that our E field is constant. What that means is that the E field here and the E field here are the same value, much like the E field here and the E field here are the same values. Now, to give you a better example of when that is not the case, let's do the same kind of situation. We have a positive charge, right? Some field lines, okay? But see what happens. See what happens when I make the Gaussian sphere, like so. All right, so here's my Gaussian sphere. So according to the formula, E equals KQ over R squared, the bigger or further away your radial distance, your E field gets smaller. So we can see here at this E field, let's call this EA, and let's call this point over here, let's call this point EB, we can say that EA is a lot stronger than EB because the radius for A is less than the radius for B. So in this case here, this is a very bad Gaussian surface, by the way, because we did not make the E field constant throughout. And so you might be thinking, well, Mr. Lee, how do I know where to place the Gaussian surface? And that's the beauty of these Gaussian objects. It is something that you come up with, much like how in the previous video I was talking about this area, like this window that you're coming up with. It's just an idea. You can place the window however big, however small, wherever you want. So instead of putting the Gaussian surface like this, you should be putting the Gaussian surface around the charged object, so that, in other words, it just makes sense, right? It's right in the middle of it. So if we do that correctly, we will have a situation where EA is equal to EB, okay, where RA is in fact equal to RB, and this is for the ideal Gaussian surface. Okay, so this is what we want. All right, now we have our new formula. I just told you how to draw a Gaussian surface around the object so that it makes sense. Now let's just go into the math side from it. All right. So if we were to determine the flux of our point charge, we can say it is the closed surface integral E dot dA, right? Always start off with the formula that you are given and the rules of integral supply. We want to pull out all the things that are constants. So remember, this dot product just means cosine of the angle. If we go back here, okay, I'll do this in a different color. So here is the E field, right? And right there is our teeny tiny window. So if you remember from the previous video, if this is our window or our area, okay, the direction of the area is always perpendicular to the surface area. So this is the direction of the area. And we can see here that the E field is going straight up through, right? And so this is what we want. We want a situation where the angle of the E field and the angle of the direction of the area gives us 0 degrees. Or in other words, the E field is going through the area, okay? And so that makes our dot product, cosine theta, cosine of 0, which just gives us 1. So I'm going to put that in parentheses here because that's important. So what we can do is we can pull out that E, because it's a constant, right? And that 1 is just a 1. So there's an imaginary 1 right there, and we get this formula here. And you might be thinking to yourself, all right, Mr. Lee, what do we do from here? Well, we know what the dA is, right? We created that dA. That dA is the sphere. So what is the formula for the surface area of a sphere? Well, it is 4 pi r squared. So we can do a little substitution. We can say E closed integral 4 pi r squared, and we can even expand this a little bit more. Okay, I'm going to replace that E with our formula from before, 4 pi epsilon naught, so that's K, Q over r squared, closed surface integral 4 pi r squared. And so from here, we can use the rules of calculus and pull out all the things that are constant. So I'm going to highlight it. So the number 4 is a constant, pi is a constant, right? And this r squared, that's what we're taking the integral of, and we're just going from 0 to r, and so that just makes it r squared. Okay, when we take the integral of r squared. And so what happens there is we get 1 over 4 pi epsilon naught q over r squared, okay? And we took out the 4 and the pi, and then you know what? I'll show you the steps directly. 0 to r, r squared, and we take the integral of that with respect to dr, and we get 1 over 4 pi epsilon naught q over r squared 4 pi r squared. And here's where the algebra takes over. We can see here that the 4 pi cancels out, the r squares cancel out, leaving us with the following formula. The flux is equal to the charge over this constant epsilon naught. And this here, that is very important. Highlight that, and we'll go into the importance of this formula in just a little bit. So important, I'm gonna write big idea. Okay, so this is a big idea, and let's just phrase it. This is the flux for an enclosed charge. Okay, this is what we get. All right, so from here, we can come up with a different scenario. So if this is the flux for a enclosed charge, what about the flux for a charge that is not enclosed? So I'm going to do a quick little detour. So if I have, a charge like so, okay, and I'm going to put my Gaussian surface. I don't know why you would do this, but we're going to put the Gaussian surface out here. Okay, we're going to put the Gaussian surface out there. So you did not enclose the charge, so you missed step one. And I'm going to focus on this E field right here. Okay, so this is my Gaussian surface. Okay, this is my windows, and we can see here that this E field, it'll go through that part of the window, but see what happens as it continues going out. Whoa, whoa, whoa. So the amount of E field going through this window, or excuse me, the amount of, so this is the flux going in, and here we have the flux going out. And this is two different windows, and that's important. This is the flux for two different windows compared to here when we just had one window, right? So this is our original idea from the previous video. This is only one window. So the amount of E field going through this one window, okay, gives us flux. But here we have two windows. So here we have flux going in, and here we have flux going out. And because of that, the total net flux here is 0, okay? And this is just for this E field. But the way that the geometry and the math works out, even these E fields, okay, the way that the angles work, the sines, the cosines, and all that, these E fields also give you a flux of 0 from the math. Okay, so every single E field that is going through this flux or going through this Gaussian surface, which does not enclose, the charge, will give you a flux of 0. Compared to if we were to have a, let's go back up to the original. Here, every single window here, we only have fluxes out, right? So here we have a flux out. Here we'll have a flux out. Here we have a flux out. So we only have fluxes out for this charge compared to when the Gaussian surface is not enclosed, you have flux going in and flux going out. So you have a net flux of 0. And this is huge. Okay, so what this tells us is if Gaussian surface does not enclose, your flux is 0. Let's see, newtons coulomb meters squared. Okay, this is ginormous. This is huge, because if you take these two, this idea and the idea from before that I highlighted, where we have flux is equal to the charge divided by epsilon naught, that's for an enclosed charge. With this idea here, if Gaussian surface is not enclosed, okay, your flux is 0. Mathematically, it should make sense, because we know that this is the derived formula for flux for a charge enclosed if you're not enclosing. So here, your Q is 0 if not enclosed. So of course your flux is 0, right? So these two ideas communicate with each other. Now, that right there is Gauss's law. Gauss's law is just a It's an idea, it's a concept to help explain how to determine. I'm saying this out loud, but I should be typing this, right? So here we can say Gauss's law. You can determine the amount of charge enclosed, okay, slash the E field, slash the flux by drawing Gaussian surfaces. Okay? So that's Gauss's law, and the best way to really represent this is from a little practice here. So I'm going to draw different charges. I'm going to draw, let's draw 4 charges. Okay, I'm going to do this with different colors eventually. So here we have positive 3Q. Here we have negative 2Q. We'll have a 5Q there, and we will have a let's do a negative 3Q. Okay, and these are just charges. I'm going to draw different Gaussian surfaces. Remember, a Gaussian surface, we want it to be symmetrical, but conceptually it works as well. So the first Gaussian surface, I'm just going to draw it like so, and we're going to call this A. Okay, so if I were to ask you, what is the flux for A, right, magnitude-wise? So you'll say it's just 3Q over epsilon naught. Makes sense, right? Because we enclose 3Q. All right, let's do one of these. All right. So here we have a Gaussian surface. Okay, notice it's not a sphere, but remember these are just ideas. Okay, so we have a Gaussian surface of B. So if I take a look at the Gaussian surface of B, we have a minus 2Q and a plus 3Q. So what ends up happening is that the E field that those two will produce, and that is enclosed by this Gaussian surface, will be the strength of as if it were just 1Q. Okay, and let's continue this train. Let's do this right here. All right, so we'll call this C. And if we have that as C, we have a positive 3Q, a negative 3Q, and a positive 5Q. So what ends up happening is that the E field that is produced has a magnitude of 5. So if we were to compare A, B, and C, we would rank the E fields that are produced as C is the greatest, followed by A, followed by B. Okay, and if we were to take a look at, let's just do one more, just to make sure we have this. If we have a Gaussian surface out here, and we were to call this D, we will say that the Gaussian surface from D has no Q or 0Q. Okay, and that's because it's not enclosing anything. And you know what? To hone in on an idea, let's do a galaxy pen one. If we were to encircle this 3Q and this negative 3Q, right, and we were to call this E, we would say that the flux of D is equivalent to the flux of E, because the positive Q's, 3Q and the negative 3Q would cancel out, and because of the cancellation, it's as if no charge is enclosed. All right, that's that. In the next video, we'll go over more shapes, more different Gaussian surfaces. I'll see you next time. Bye-bye.